All right. For our final unit in the properties and attributes of functions, we're going to look at parent function identification. First group of functions we'll talk about are the polynomials. We looked at these in the first semester. One of the characteristics of polynomials is the end behavior, that the limit wouldn't phrase it that way. We would say that as x goes to, and I'm going to generalize this, both positive and negative infinity, the functions themselves go to either positive or negative infinity. Okay, so we don't have that horizontal asymptote kind of behavior going on the polynomials on either side. So they also tend to be kind of wiggly. They have the potential to be that way anyway. So qualifying as polynomials would be like our linear functions. So if it looks like that, it's a polynomial, and we can specify by degree all that stuff that we looked at back then. This would be a degree 1. We know that we can get things that look like that. Is a parabola, that's our polynomial with degree 2. A degree 3 polynomial might look something like this. It doesn't always have to look quite that wiggly, but it certainly could look something like that. And we'll throw a degree 4 on there as well. So our degree 4 has the ability to wiggle even more, but the end behavior way up to the left and way up to the right is always getting either toward positive infinity or negative infinity, and the same thing off to the right, either towards positive infinity or negative infinity. Okay, so those are the kind of shapes that we expect to see for polynomial functions and polynomial data. One other unique characteristic of those is something called common differences. A difference is a subtraction problem, an answer to a subtraction problem. So the first thing we have to check is when we're looking to see if this might be polynomial data, is to look to see that the inputs are evenly spaced. Okay, so this goes plus 4 every single time. If we don't have that, then we're going to have to try other things. But if we have equally spaced inputs, then we can start looking at the outputs, and a common difference. What we're going to do is look here and here, and we're going to do negative 2 minus 30, which would give me a negative 32. 190 minus negative 2 is 192. 990 minus 190 is 800. And 2782 minus 990 is 1792. Now, these numbers in blue there had been all the same. That would have told me that this was linear. Okay, if the first differences were equal. If I can spell first. Okay, and I'm going to use the right color. So, first differences, if they are all equal, then this is linear. That's not the case here, so we're going to try again with these sets of numbers, and I'm going to do 192 minus negative 32, so plus 32, gives me a 224. 800 minus 192 is 608. And 1792 minus 800 is 992. These are my second differences. If the second differences were all the same, that would tell me that this data is quadratic. Okay? Clearly is not. We're going to try this one more time. 608 minus 224 is 384. 992 minus 608 is 384. Okay. This is my third differences. My third differences are equal to each other, this indicates that this data would be fit by a cubic function. Now, if it didn't match there, and I tried to go any further, I'd only be down to one data point, which I couldn't compare it to something else. And that's where I would have to be a little bit careful on this, is that if you go far enough on these first, second, third differences like that, you're eventually going to get down to one thing, which indicates that that would fit perfectly, and you can get a function that will go through all of the points, but it probably isn't going to match the shape or predict the way that you would expect to. Okay? So the warning here is that you can always make a polynomial fit if you have a high enough degree on it. But there has to be a reason for choosing a degree that high, and the actual shape, when you look at the data, should match the shape of that polynomial that you're trying to fit there. Okay? So there are very few real-world situations where a degree 7 polynomial is actually the right model for something. There's just not situations where that is a meaningful thing. So we have to be a little bit careful with how excited we get about applying polynomial models, unless there's some reasoning behind it that makes sense. All right, exponential functions. The end behavior of our exponential functions, we know that one side is a horizontal asymptote. And the other side either goes to positive infinity or negative infinity. Okay, so that is something that doesn't happen a lot of different functions, but it is characteristic of exponentials, and so that's one of the things that we look for and we see. The other thing that we notice if an exponential function is that we have no high points or low points, so we have no maximum and we have no minimum, no hills, no valleys. All right, we're accustomed to this kind of shape, right? Or this kind of shape. And one side goes off to infinity, and we can reflect it, and it could go the other way as well, but one end behavior is toward infinity, the other end behavior is a horizontal asymptote. Right? Exponentials, we also talk about these separately because they have this characteristic called a common ratio. Ratio means right a fraction, right? And so the same kind of idea here, we're going to do the 10.45 divided by 9.57. When I do that, I get a, make sure I put that in right, yeah. I get 1.0919, right around there. 11.41 divided by 10.45. I get a 1.0919 approximately. Okay, it's not exact. I'm doing a little bit of rounding, but keeping at least 4 decimal places here. 12.46 divided by 11.41. Things are looking pretty good so far here. This gives me a 1.09, actually 20, which is not exactly the same, but not far off. And this last one, the 13.61 divided by the 12.46, actually gives me a 1.0923. So it's starting to get a little bit different, but overall that could be attributed to rounding errors that are in this. And so since this common ratio is pretty much the same, be enough to say that an exponential model would probably be a good predictor for what's going on in there. Okay? So, other parent function shapes that you should be familiar with. Okay, this was our reciprocal function. Okay, we see that it has horizontal asymptotes on both ends. Okay, so as x approaches both positive and negative infinity, the f of x, I'm going to write that on another line because I'm kind of crunched in here. The f of x approaches a number. Okay, that's a horizontal asymptote, and it also has a vertical asymptote. So having both vertical and horizontal asymptotes is characteristic of a reciprocal function. Okay, this is a logarithm, or a logarithmic function. Our logarithmic function has a vertical asymptote so we got the vertical asymptote, and then we have our end behavior actually as is really only one-sided end behavior. Right, we'll either be able to talk about what's happening as the x goes to infinity or as it goes to negative infinity, but it can't do both. We have a very restricted domain on the logarithmic function, which was unique to that for the types of things we've looked at. This one is the absolute value function. We have not spent a lot of time talking about this. You can see that its big major characteristic is that it's got a sharp corner in it. We haven't come across any other functions that have a corner like that in there. Okay, and so that's something to look out for if it's going to be an absolute value function. And then finally down here, this is a square root. We haven't looked at square root as a parent function to this point, that is coming, but just to begin familiarizing ourselves with that, we can see that this has, it just seems to kind of start out of nowhere, right? So we can say that it begins right there. That's all that it is. So it starts out of the blue or out of nowhere. Just seems to kind of pop into existence there and then go off toward infinity. Not a lot of high points or low points in that one either. In fact, it looks like and is half of a sideways parabola. So that's kind of what is how we recognize the possibility of that square root function. So once we've identified the parent function, we've maybe got some points to work with. How do we come up with an equation for it? Well, we've got to know something about our general forms, and the general forms come back to knowing that, okay, if I recognize whatever my parent function is, okay, I typically can get away with saying I'm going to have some kind of vertical stretch is a possibility. So maybe I'll say, let me multiply by a, and then possibly a vertical shift. I'm going to make that a plus k. There could be a horizontal stretch or compression. I'll do that as a times b. And there could be some kind of horizontal shift. I'll do that as a plus h. And so looking at what a general form might look like outside of some of our polynomials, there treating it a little bit differently. But if this is just some movement of the parent function, then this should cover those possibilities. And so working this parent function in with x minus h over b, put that into the parent function, whether that is an absolute value or a square root or the reciprocal or whatever might be going on there, and then do the vertical stretching that we might need to do, and then shift it up and down if that needs to happen. If you entered something like this into Desmos, again with referencing a specific function, not just an f in there, then you should be able to match if you've got the right thing. Okay. In polynomials, our thing with polynomials is they could look like, if we're the notation that would go into Desmos, y1 is equal to a times x1. Say we wanted it to be a cubic, then we're going to do that cube plus b times x1 squared plus c times x1 to the first power plus b, and that should find values of a, b, c, and d for us in Desmos. Okay. So lots of information on there. It's all stuff that we're going to continue to use and work with along the way, but this is going to wrap up our discussion of properties and attributes of functions at this point, and then we'll get ready to move into something else. But all of this stuff is going to come back and be important.